A blast furnace is more than just a vessel. It is a 15-year commitment or plus, 15 plus year commitment. The decision we make during the first 168 hours of a campaign dictate whether we achieve a decade of stability or a series of premature failures. So today we are looking at the fundamental operation of commissioning, moving from final refractory dry out to first critical cast of hot metal. By the end of the session, you will master three core deliverables. First, the thermodynamic requirement for refractory stabilization. The second is the structural logic of hearth. And the third is the precise chemistry engineering required for the initial burden. Observe the blueprint on the screen. It represents the complexity of the giant we are about to wake. Note the intricate gas cleaning network and the massive hearth foundations. Understanding the system as a unified reactor um, is the first step towards a successful startup. So, to understand the operation, we must first master the physical anatomy of the vessel itself, and that is one of the most important. So on the left, we see a cross section detailing the five key zones: the throat, stack, belly, wash, and hearth. We are transforming a cold moisture laden shell into 2000 degrees centigrade continuous thermochemical reactor. So look at the table on the right. Our work volume here ranges from 1462 to 3274 cubic meter with 20 to 32 tuyeres or air injection points and 2 to 3 or even 4 taffles for liquid extraction. The shear scale is daunting. The so what is very simple. So if you initially blow in is imprecise, you risk uneven thermal expansion. This can lead to a premature refractory wear in the Bosch or uneven gas distribution in the stack. So this is why the first take with a success is required. So we are aiming for a campaign life of 15 plus, and that clock start tickling the moment we introduce the hint. So precision now prevent catastrophic capital loss later stages. The very first step in this journey is removing the one element that can destroy our new lining, and that is really very important. I know everyone knows, and that is water, water, water. So coming to the uh, dry out, so we have to focus on the diagram on the right. The orange arrow represent the migration of moisture through the brickwork. We are managing two distinct phases: physically bonded free moisture, which lives at temperature below 150 degrees centigrade, and chemically bonded water of crystallization, which require 300 degrees centigrade to 800 degrees centigrade to extract. So we execute this through gradual ramp rate of 15 degrees centigrade to 25 degrees centigrade per hour using hot blast air or portable Dutch oven. So why such a slow pace? So if we move too fast, then the internal steam pressure exceed the tensile strength of the refractory, leading to a spalling, or effectively the brick explode from the inside out. So a dry out stage is a really very important and is a death sentence for the heart. So we must ensure the calcium aluminate cement phases are fully cured before the first coke charge ever touches the floor. So once the moisture is gone, we must secure the furnace against the hazard of oxygen and the leak. And this is of the phase 2, which talk about the system purging and pressure testing. So follow the blue lines in the technical schematic on the right. This is the gas cleaning and cooling network. So we use nitrogen or steam to purge the system, creating a positive pressure environment that completely displaces oxygen. So as you in the circular inset, we apply soapy water solution to every flange and joint. So we are looking for zero bubble at pressure between 3 to 4.5 bar. So the operational impact is non-negotiable. We must eliminate the risk of explosive hydrogen oxygen gas mixture. Furthermore, we must verify that our cooling steps and plates have zero water ingress into hearth. Even a minor leak during the blow-in can cause a hydrogen explosion or chill. Uh, it cool down the hearth before the first cast, so potentially leading to a frozen furnace and total disaster. So with a sealed and dry vessel, we move inside for the manual architectural phase. So coming to our next slide, which is focusing on our phase 3, that is a heartwood feeling. So look at the 3D cutway on the right, that is lumbering, the manual stacking of roughly 200 cubic meters of timber in the crucible. Note the log cabin pattern. The sleepers are stacked at 90 degrees angle. This architecture provides immense structural stability to support 100 ton of coke while guaranteeing a high zero permeable zone. So these would serve two purposes. It acts as a low temperature ignition bridge between the hot blast and the coke, and it protects the newly dried hearth floor from mechanical impact of falling burden during charging. So follow the wooden sleeper towards the tap hole. We ensure a clean gas path so that the first molten product have a way out. Without this permeability zone, the furnace would suffer from high pressure and poor gas distribution right at the start. So once the wood is set, we begin the high stack process of strategic first fill, and this is we can observe by the layering in the vertical furnace diagram. At the bottom we have the wood followed by a massive coke blank occupying 25 to 40% of the working volume. So this coke blank has a thermal reservoir. Above that we see flux coke layer and the right burden where the O to coke ratio is strictly held low around 0.5 to zero point 0.6. The so what factor here is the slag chemistry. We are targeting an alumina content of less than 13 to 15%. If someone asks why, then because in the cold startup you need a highly fluid slag to prevent a viscous freeze. If your initial slag is too uh, mm, thick, it would not flow to the tap hole, and you will end up with a chilled hearth that could take weeks to recover. So, with the burden in the place and the chemistry set, it is the time for ignition sequence, and which is about the phase number 5. So look at the graph on the right. The y-axis represents wind volume as a percentage of normal, and the x-axis track our first 7 days. We ignite the kindling using hot blast air between 550 degrees centigrade and 650 degrees centigrade. So notice the steep initial climb followed by a more measured ramp up. We operate strictly on natural draft for the first 24 to 36 hours before stepping up the wind. So our operators are consistently and continuously monitoring the blowing factor, the relationship between the blast pressure and the wind rate, to gauge how well the furnace is digesting the raw material. We are pushing the hearth beyond 1500 degrees centigrade, but we will must do so cautiously to avoid channeling where gas bypasses the burden, or hanging where the material stops descending. Now coming to the our transitional slide, which is about roughly 24 hours of successful ramp up, we reach the most celebrated milestone, and that is the phase 6, the first tap. So this visual capture the moment of truth. The first cast typically occurs 20 to 28 hours after ignition. You will see operators watching the taffel for gas puffing. That rhythmic pulsation is the primary indicator that liquid slag has a accumulated. So once we see that the hole is plugged with a mud gun, so note the target chemistry. We are looking for high silicon iron between something around 2 and less, and here it is 2.5 and less. So this is yeah, intentional. So high silicon content ensure metal stays hot and fluid in a steel warning hearth. So these first cast clears the crucible of accumulated liquid, preventing a catastrophic freeze up. So it is the definitive proof that our thermodynamic calculation for the coke blank and the wood filling were correct. So to visualize the entire sequence at a glance, let's look at the blow-in synthesis matrix. So coming to the our next slide, which is on this matrix. So this matrix summarizes our entire campaign startup. So look at the critical risk mitigated in column. So for dry out, we stop system explosion. For purging, we stopped S2O2 combustion. For the first field, we engineered against a viscous slag freeze. So, so each success milestone on the right represent a gate we must pass. If you do not achieve the 50 to 25 degrees centigrade ramp rate in dry out, you do not move to the purging. If you do not see zero bubbles on the flames, you do not start changing or charging. So this is not just a checklist, it's a structural and thermodynamic hierarchy. Each phase builds the safety margin for the next. The operational impact of blowing this matrix is difference between a furnace that struggle for a month and that one reaches rated capacity within its first week. So as we conclude, let's remember the long-term perspective of these first few days rather. So a foundation for the decade, and we have covered the log cabin architecture of the wood fill, the chemistry of the coke blank, and the decade. So 7 day wind up and ramp up as this final visual of glowing hearth reminds us the blow-in process is a high stack choreography of thermodynamics and fluid dynamics. So a meticulously executed startup dictate the campaign life and the fundamental safety of the mm, of this asset for the next 10 to rather 15 years plus. So you are not just starting a machine, you are stabilizing a giant. So and the success totally depend, and for that we have to a combination of knowledge as well as you have to combination with our procedures.